Hi, everyone. Welcome to this month's webinar. I'm Aaron Hill, and I'm Vice President of here at Sawtooth Software. Today's webinar is Pros and Cons of Market Simulations using Randomized First Choice versus HB Draws. And our presenter is Brian Orm, President of Sawtooth Software. Brian's been with the company for about 25 years, so if you're familiar with Sawtooth Software, or if you've read through our documentation or attended any of our conferences, you've had some interactions with Brian. During the webinar, please use the Q&A window to ask questions, and we'll answer some of those during the session. Some we'll answer offline by typing in answers, and some we'll answer during the presentation or afterwards. We'll also be sending out a link to the recording and a copy of the slides to everyone when we're done. So those will be available on the same website where you signed up to attend today's session. Usually that happens within 24 hours. Occasionally it takes a little bit longer. So those will be available to you after the session. So with that, Brian, the screen is yours. Take it away.
Thank you, Aaron. And thank you everyone for coming and visiting us for this webinar. This webinar is going to be a little bit more advanced than most webinars that we give. It'll especially be meaningful for you if you spend very much time thinking about the math behind market simulators and how to make it better. Or if you end up building a lot of simulators in something like Excel, I think that what we're going to be talking about will be of interest to you. We're going to be talking about, of course, the comparisons between using randomized first choice, which is Sawtooth Software's default, but not only market simulation approach, versus hierarchical Bayes draws. So on the agenda, we're going to review what the red bus, blue bus issue is, also known as IIA. We're going to talk about how randomized first choice works and how it deals with IIA to help combat it. We're going to review what HB draws are and how you might use HB draws in your simulators. We're going to make some practical comparisons with some data sets and some different types of simulations, looking at the share inflation issue for similar or identical products, as well as sensitivity simulations when we simulate, for example, demand curves using market simulators. We'll wrap it up with some conclusions and recommendations for practice. As a brief review, market simulators use conjoint utilities, usually estimated at the individual level via something like hierarchical Bayes, to predict what respondents would do in new market scenarios where we specify two or more products that would be competing with one another, where those products are defined on the attributes and levels that we included in our conjoint analysis study. In the simulator, we have each respondent, assuming we have hierarchical Bayes utilities, vote for the preferred product out of the set of products that we've presented to them, if you will, in the market simulation scenario. Splitting the votes rather than the first choice rule typically is more true to the logit models, especially hierarchical Bayes logit, that were used to estimate the utilities. When you think about what was going on with hierarchical Bayes, is it was trying to maximize likelihood via the upper and lower level models, it was doing so using the logit equation, also as what we know as the share of preference rule. So whenever we can build simulators, of course, that are following the same logic as the way that the utilities were estimated, then our simulators are more congruent with the way that we estimated the utilities. So we do like the idea of splitting votes somehow. IIA, also known as the red bus, blue bus issue, is something that was pointed out clear back in the 1970s. The early choice modelers were running logit models on people's choices for transportation within cities. These weren't conjoint experiments where we were experimentally developing a bunch of profiles and showing respondents in a survey. Rather, they were collecting information about where respondents existed and their characteristics, and then asking them what choices they were making to get places within cities. And they were taking that revealed data, if you will, about past behavior and modeling it using conditional logit, also known as multinomial logit. The practitioners of the day in the 1970s recognized that the logit model had a known property called IIA, also known as independence of irrelevant alternatives, which made it estimate well, but also it was a limitation, and it had a property that says that the ratio of any two alternatives in a choice set their likelihood, that ratio, is independent of any third or fourth or fifth alternative that comes and enters the scenario. So in other words, if we were thinking about Coke versus Sprite, that maybe that's a ratio of 2 to 1 of preference, and a new entrant such as Coke Light would be viewed to take equally from Coke and Sprite, proportional to the previous shares, resulting in keeping that ratio between Coke to Sprite equal. And that implies constant substitution rate, which is unrealistic when we think that different brands will compete more strongly with other brands, etc. So IIA assumes that constant substitution rate and can lead to inflated shares for similar or identical product offerings. They call it the red bus, blue bus problem because early transportation researchers were working on transportation research where they were thinking about ways people get to work or get around the city, such as cars, trains, walking, biking, and busing. And they could show that by putting all of those alternatives into a competitive scenario and using the logit coefficients, they could predict what people would do by varying the characteristics of the people or the ways of transportation. When they doubled up the buses on an unimportant attribute that should make no difference to people, such as the color of the bus, they found that the net share for the two buses would nearly double, which is a problem because you'd expect by doubling the number of buses, by making, or not doubling the number of buses, but by making half the fleet red and half the fleet blue, such that there was a choice between red and blue, shouldn't really make a difference between whether people are taking buses or cars or trains or walking to work. And so to deal with that problem in the 1970s and 80s especially, researchers who were interested in slaying the IIA dragon would build cross-effect terms into their models as new utility terms, and this would make their models grow with a lot of terms added to the model, with potentially a lot of overfitting and sign reversals and problems that ensued, especially with small sample size. Well, transport yourself back with me 22 years ago when I was at Sawtooth Software and sitting and thinking about this problem. At the time, Sawtooth Software was just getting ready to release hierarchical Bayes for CDC, but most modelers at that time, most Sawtooth Software customers and others, were still using aggregate logit or the new kid on the block at the time, which was latent class multinomial logit with perhaps a 4, 5, or 6 group solution. And most people were building market simulators based on these low dimensionality latent class solutions or single dimension aggregate logit. And under those simulation tools, under those vectors of utilities that you had, when you started adding multiple buses or a Coke and a Coke Light, you'd see this problem with IIA, and share inflation for similar or identical products was a big, big problem. So I thought about it and came up with a solution back in 1998 called Randomized First Choice, which I'm going to explain to you in a minute, that penalizes products that share lots of attributes or multiple attributes in common. How randomized first choice works is that the unit of analysis, and the unit of analysis, if you're running aggregate logit, would be the population. It would just be a single vector of utilities representing the population. If the unit of analysis is segments from latent class, then segment 1 is a unit of analysis 2. If you're running hierarchical Bayes, the unit of analysis, we have a vector of utilities for each respondent. So whatever you have, randomized first choice can apply to all 3 situations. You take that unit of analysis and you send it on multiple shopping trips or multiple iterations where the unit of analysis, whether it's this population, the segment, or the respondent, makes a first choice vote in each trip according to the part worth utilities and which product alternative out of the set in the simulation scenario is best. Now, to make sure and to make this work so that we can split the votes and not just have the unit of analysis pick the same thing every time according to the first choice rule, in each shopping trip, the utilities are perturbed by random error. Now, we typically use normal zero-centered error, but you can use other types of distributions, and they also tend to work really quite well within the randomized first choice methodology. Let's describe how this works. Let's imagine that we have a unit of analysis. Maybe this is a respondent. And this respondent set of utilities are in this first column. This would come from hierarchical Bayes or something like that. And in this simple example, so that we can put it on the screen easy, we just have two attributes: flavors of ice cream and the form factor for ice cream. Now, this respondent slightly prefers chocolate and slightly prefers cones over cups and bowls, etc. And the utilities are zero-centered, although they don't necessarily have to be for randomized first choice to work. Now, the typical situation is that we set up a market simulation. And we have this simulation scenario where I've decided to put in 3 products in competition with one another: a chocolate cone, a chocolate cup, and a vanilla bowl. And as you know, what we do is we take the part worth utilities. To figure out what the total value of the chocolate cone is, we take the chocolate component, the part worth, plus the cone part worth, and that equals the total utility for chocolate cone. And we do the same thing for chocolate cup and vanilla bowl, finding that for this respondent, just from the hierarchical Bayes utilities, we would predict, according to the first choice rule, that they would prefer the chocolate cone. Now then, we're going to send this unit of analysis, this respondent, on multiple shopping trips. And in each shopping trip, in each iteration, we are going to add to the part worth utilities some attribute type error, typically distributed normal, and these are represented in green. So we've drawn this vector of random variates here that we've added to the deterministic part of the utility to get a total perturbed utility in iteration number 1. Now, it turns out that these perturbations weren't different enough to really shake this person from liking chocolate cone better than the other 2 alternatives. But you can see in the second iteration, the random draw, the vector of random perturbations is going to change it so that this person prefers the chocolate cup in that iteration slightly more than the chocolate cone. And so in that case, the person votes for chocolate cup. And we'll typically repeat this hundreds or thousands of times and then add up all of the first choice votes across the iterations for this respondent or the unit of analysis, if it's at the segment or the population level, to split the votes and come up with our shares of preference, which we report in the simulator. So that's how randomized first choice works if we're only applying attribute type error, which is the default in our software. Now, how this corrects products that have similarities is that if 2 products share a lot of the same levels, then a lot of those green numbers are going to be shared in the iterations. In other words, for example, if we go back, you can see that every time chocolate cone and chocolate cup are simulated, there's a chocolate random draw that affects both of those. Chocolate cone and chocolate cup share this little random component, but they have a different random component perturbation coming from the form factor. So chocolate cone and chocolate cup share essentially a half of the random variance in every iteration, causing chocolate cone and chocolate cup to, in essence, kind of dogfight as it goes iteration by iteration and to more closely compete with one another. If you were to look, and I simulated this out for 100,000 simulated iterations, chocolate cup and chocolate cone share a half of the random component, the chocolate component that gets a random variate every time, leading to a correlation across the iterations of a half between chocolate cone and chocolate cup. Now, if we had more attributes in the model, let's say 5 attributes in the model, and 2 products shared 4 of the 5 attributes, then the correlation would be 80%. So the more attributes that you share in common with another product alternative, across all the iterations of the randomized first choice process, the correlation increases. And 2 product alternatives like vanilla bowl and chocolate cone, which don't share any attribute levels, are correlated 0 across the iterations. And this correlation that we impose due to shared attribute levels through the randomized first choice process is what causes the tamping down or the correction for similarity to penalize the utility, the shares of preference for products that share multiple attributes in common. Okay, now you might say to yourself, well, great, Brian, how do we decide the variance of those green numbers, of those random variates to add in each in each iteration, because if we used a really low variance on those, in fact, if we used a 0 variance, then we would just replicate the first choice rule every time, because we would just have the deterministic part of the utilities, and the respondent would make the same first choice every time. However, if we added a really high variance vector of random perturbations to the utilities, that would essentially swamp the signal and essentially flatten the shares out to 1 over k, where k is the number of alternatives in the simulation. So what do? Well, if you're using Sawtooth Software's tools, we automatically tune the variance by looking at the number of attributes involved and the number of products in the simulator. We tune that variance so that we'll get a similar scaling, flatness or steepness of the shares, as would be expected from the regular logit share preference simulation model. And we've done all of those simulations and that tuning ahead of time so that you don't have to worry about it. But you can, in the software, go in and override this with your own tuning. You can say, hey, look, I want to tune up a little bit steeper, or flatter the model by changing the amount of the variance of the attribute type distributed error. Now, by default, attribute type error is the only error that we impose in randomized first choice, because that's the type of error that if two products share exactly all the same attribute levels, will exactly split the shares in half if two identical products are put into the simulator, leading to no share inflation. However, there is an advanced option that you can click into in our software by clicking the little gear button next to the randomized first choice setting to tune an additional type of error that we add at the total product level. After adding up the attributes and levels across the part with utilities and the any random components from the attribute type error, we can add an independent and identically distributed, and we typically use Gumbel distributed error at the product level for each product independently. This allows us to start to influence the randomized first choice results with a little bit of IIA if we want it, because some degree of IIA might be useful for certain markets and certain simulations and better reflect real-world purchases. In reality, respondents have some random aspects to their behavior, and if we were to put out an identical product and make it available, let's say on another aisle of the supermarket, it's likely that our total volume that we sell, our market share is going to go up just due to duplicating the product and making it available in another part of the supermarket, for example. Because some degree of random behavior happens as people see stuff, they say, oh, I see it, I like it, I pick it up, et cetera, et cetera. So given that we can tune in randomized first choice the contribution and the variance of the attribute type error and the product type error, it turns out that randomized first choice is very tunable, and the share of preference, the regular logit equation, and the first choice rules are just special cases of randomized first choice. In the first case, if we turn off the attribute error, and the only error that we add is Gumbel distributed error at the product level, and that's consistent with RUM or RUT theory, as those of you might know that, it turns out that after iterating out hundreds and thousands of times or millions of times, that converges on the standard, what we get from the logit equation. So with randomized first choice, we can reproduce what happens in the logit equation by turning the attribute error off and adding just product type error. On the other hand, we could replicate the first choice rule if we turn both types of product error off and tune them to have a 0 variance on those random variates. Then we can produce the first choice rules. So randomized first choice is extremely tunable to correct fully for products that share all attributes in common, such that we perfectly split their share to have no share inflation, or we can have the regular type of share inflation due to IIA if we tune randomized first choice to only add product type error. That said, hardly anybody ever tunes the error, I think, other than using Sawtooth's default of attribute type error only, meaning that they want to have a full correction for similarity if two products share all of the attribute levels. Now then, that is randomized first choice, but let's talk a little bit about hierarchical Bayes draws. Most of us use hierarchical Bayes just by taking the average of the draws and having a single set of utilities, a single vector of utilities for each respondent. But we know that in each iteration, HB produces a proposal, a draw for each respondent's utilities. In fact, if we've run 20,000 burn-in and 20,000 used iterations, we have a total of 40,000 draws. We would ignore the first 20,000 draws, and we might think that we could use the last 20,000 draws. Rather than just collapsing and averaging those 20,000 like Sawtooth normally does, you could think about writing those out to a file, and Sawtooth will allow you to write and save out those draws to a file and just use those last 20,000 iterations, those last 20,000 draws, which have a lot of difference from draw to draw if you've ever looked at them, okay? So what you could do is to make the file not so big, you could sample, let's say, 100 or 1,000 draws evenly across those 20,000 used draws for each respondent, and simulate each respondent's choice 100 or 1,000 times by representing them in your simulator 100 or 1,000 times as different rows in the simulation data file. And in each of those simulations on each of those draws, we could either apply the share preference, the logit equation rule, or the first choice simulation rule. Now, when you think about it, randomized first choice is kind of poor man's draws. Randomized first choice draws are independent and identically distributed with no correlation of errors across different levels within the same attribute within the unit of analysis. So when I'm a respondent, and if I have, let's say, Diet Coke and Coke Zero as two levels of brand, every iteration of randomized first choice is going to give me an independent, non-correlated draw of Diet Coke and Coke Zero, because randomized first choice sees those as two different levels of an attribute. So therefore, to randomized first choice, they must be different. Okay. In contrast, if you were to look at the hierarchical Bayes draws, and if you were to have two levels of an attribute like Diet Coke and Coke Zero, it's very likely that you'll see a high covariance or correlation across the draws within the same respondent, because the HB draws have a lot of are influenced a lot by the upper level covariance matrix. Remember, at the upper level, we're estimating at the population level the means and the covariances. Well, the means and the covariances have a very large influence on the means and the covariances at the respondent level. And thus, what's nice about the draws is that two levels such as Diet Coke or Coke Zero, two levels of brand, will be seen to be correlated in preference through the pattern of draws that tends to mimic and echo the upper level covariance matrix. Now, randomized first choice has a very simple view on similarity. Randomized first choice says that two products are only similar if they share some attribute levels in common. And if they don't share attribute levels in common, then they get independent variance draws, independent draws of random error across each iteration, okay? So two levels of the same attribute that respondents might perceive as substitutable will still be treated as unique by randomized first choice. And the only, but of course, as you know, across respondents, that's within the unit of analysis, but across respondents, because you have Coke people and you have Pepsi people, across respondents, just due to the heterogeneity and the patterns of preference, there are other interesting things that can happen that mean that randomized first choice can still recognize that Coke people like Coke products and Pepsi people like Pepsi products just due to the main effect utilities that they have. Okay, of course, academics, especially Bayesian statisticians, prefer the draws because they are true to the HB model. When you think about it, there's nothing in the HB model that says that you can take the average of all of those last 20,000 draws and that they have some sort of good fit. When HB was developing its fit and rewarding draws that got us closer to maximum likelihood, balancing the upper level model and the lower level model, it never was thinking about the average of draws. It was just thinking about the independent draws. So averaging across those is convenient, but it really departs from hierarchical Bayes and its true and the likelihood equation behind it. Nonetheless, we as practitioners have found that the point estimates work really, really well and are super convenient. Okay, so simulating using the draws would preserve the proper uncertainty in the data. The more uncertainty in the data that we have, the fewer choice tasks per person, or the more that the respondent is answering with noise, the more variance we'll see across those draws for that respondent. And the draws also reflect the proper correlations as echoed in the upper level covariance matrix. Okay, so these draws seem to potentially have a lot more information that academics say that we shouldn't be throwing out by just simply collapsing across them. We've done, clear back in the late 1990s, Rich Johnson, our founder, did some research about looking at whether that additional information in the draws really was all that meaningful and provided much more than point estimates. And he concluded at that time that, you know, although it might be academically more proper to simulate on the draws, it didn't seem to add too much to the picture in terms of what we derive from the model and the conclusions that we make, and the quality of the insights that we deliver to our clients. And I've repeated some of that work most recently in the last few weeks that I'll be sharing a little bit later in this session. Draws, of course, although they make the Bayesians happy and academics happy and are more true to the HB model, they're just less convenient because they can lead to a lot longer simulation runs and larger file sizes. Because randomized first choice is built natively within Sawtooth Software simulation platforms, we've optimized the code to run very, very quickly. And so randomized first choice runs a lot faster than if you were to do the same number of iterations and simulate on the draws. That said, those who like to use draws can try to find a nice middling ground by not using very many draws for each respondent. Perhaps 30 or so evenly sampled draws over the used draws can be used, leading to reasonable file sizes and simulation performance if you're delivering simulators, for example, in Excel. So instead of 1,000 records for 1,000 respondents, you might have 30,000 records for representing each respondent 30 times with 30 different vectors of utilities representing those sampled draws. But clients like to see one set of utilities for each respondent. They don't like to know that the respondent is actually represented by 30 different sets of utilities, which could be meaningful to them if they want to run crosstabs or something like that. So which approach practically works better, simulating on randomized first choice versus HB draws? Well, for practitioners, we mainly care about the predictive validity of the results. We don't care so much about the elegance of the theory. So we just care when the rubber hits the road, how are we going to serving our clients well? Are we going to be serving our clients well with simulating on point estimates and using something like randomized first choice, or are we going to need to do something fancier and a little bit harder, which is simulating on the draws? Back in 2016, we held a modeling competition where we created a data set, we collected a data set that had super strong properties for being able to discriminate between different models in terms of predictive validity, because it had a lot of holdout data. We had 600 respondents for whom we estimated utilities on 6 attributes for vacation choices, and we had 600 out-of-sample holdout respondents. We randomly selected respondents to be either the calibration respondents for whom we'd estimate utilities or the holdout respondents. The holdout respondents got 21 fixed holdout CBC questions, meaning the CBC questions were the same across all 600 respondents, each with 4 alternatives. Now, in each of those 4 alternatives, we created scenarios. We created the design for those 21 fixed holdout tasks such that a pair of the concepts were quite similar. They shared a lot of levels in common across these vacation choices across the 6 attributes. So they might share 3, 4, maybe even 5 levels in common for that pair of alternatives. So this is an excellent validation data set. Excellent in the sense that it has ample sample size. Excellent because it has truly out of sample holdout respondents, which is superior to having in-sample holdout respondents, and also very superior because we have 21 scenarios that we need to predict and accurately predict, each having 4 alternatives, where a pair of alternatives within each have been designed to violate IIA. Okay, so it's so we ran our market simulator based on hierarchical Bayes, and we predicted the shares of choice for the holdout respondents for the 21 times 4 or 84 probabilities for those product alternatives across the 21 choice sets. When we run a correlation, a simple correlation between the 84 predictions versus the actual 84 probabilities for those 4 times 21 product alternatives in the holdouts, we find that running share preference on the using the logit rule on the draws gives us a correlation of prediction of 0.9092. Almost imperceptibly different from it, we see randomized first choice on the point estimates at 0.9073. And doing really, really nicely, but falling a little bit behind, is share preference logit rule on the point estimates. But notice there's just not a lot of difference. We're talking about the difference between 0.91 and 0.90. And this should tell you that even in situations where we're predicting 4 alternatives in a market simulator, where some of the alternatives are quite similar, sharing a lot of levels in common, the regular share preference logit rule on the point estimates does quite decently. But the randomized first choice does a little bit better, and HB draws maybe a tiny bit better, but maybe that's just not enough difference to really make much matter of at all. Okay, now you might ask, well, where we could run first choice on the draws. That would be more akin to the randomized first choice approach, but we'd be running first choice on the draws. Why didn't we do that? Why didn't we show those results? Well, it turns out that in each of these 3 simulation runs, we tuned the exponent, okay, the exponent to maximize the R squared. And because tuning up a share preference logit rule can essentially approach the first choice model by just making a big exponent, a large exponent, much larger than 1, the default of 1, it turns out that that first choice on the draws just can't beat share preference on the share preference on the draws, because we tuned share preference to maximize the R squared, and a really high tuning would have essentially taken us to the first choice rule. Now, how did we simulate on the draws? Well, we could have built an Excel simulator, but we had already had all the scenarios set up in Sawtooth Software Simulator. So we tricked our simulator by taking the draws file and just in a couple of minutes making a couple of changes to a few columns to give it the same format as a regular utilities file that we would read into our simulator, thus tricking our simulator into reading the draws. And to thinking that there were a lot more respondents than we had. Of course, the share preference were correct because we just run the share preference or the first choice rule on each of the draws, and we roll those all up, so that's correct. But the standard errors in the 95% confidence intervals would have been incorrect as reported in our simulator, because the sample size would have been vastly overstated. Okay. Since then, we've taken that same data set that was used in 2016 for the modeling challenge, and we looked at how it could handle the share inflation issue when you take 2 identical products and you introduce them into a simulator and compare them to what happens when you just introduce one of those products in the simulator. That is the share inflation for identical products issue. We also took a look at how using these different simulation models, randomized first choice, share preference on the point estimates, or share preference on the draws, how that works when we set up price demand curves via sensitivity analysis, because there are some interesting gotchas that I want to make you aware of that will shape how you think you want to deliver simulators to your clients. Let's first take a look at the share inflation for duplicate products. In scenario number 1, we put 6 product alternatives. These are vacation choices on 6 attributes. And product one, the first vacation choice, we put in a kind of a bad one, and it only got 3.32 share of preference across the 600 respondents. In scenario two, we repeated that same simulation scenario, but we added a seventh product that was just a duplicate of the first one. And we wanted to know how the net share that would be predicted for products 1 and 7 in the second scenario would compare to just when that product was put in one time in the simulator. And here are the results. Starting at the top, if you use randomized first choice recognizes that those two identical products share all 6 attributes in common. And so it will perfectly penalize those and split their shares, allowing for 0 inflation when we add that 7th product to the simulation. It just doesn't change the simulation results. Those two identical products get the same share that they would have if they were just represented once. Now, if you use HB draws and you do the first choice rule, you also see in that second row that you get 0 inflation because it's applying the first choice rule on the draws. In the third row, we find what happens if we do what the software recommends, which is to turn off the correlated error for price. In other words, on the price attribute, we draw an independent random variate to shock the price part worths independent for each of the product alternatives. And that is what's recommended in our software, and our software will complain to you if you don't do that. And I'll show you in a little while, in a moment, why we do that, because it can create some weird kinks in sensitivity price demand curves if you don't. But when you turn off the correction for similarity for the price attribute, one of those 6 attributes becomes independent, and therefore 2 products that are identical will get 25% inflation of their shares. HB draws on the share of preference rule, okay, the logit rule would give us 43% share inflation. HB point estimates was what you typically might do if you're building a simulator in Excel and using the logit share preference rule on the point estimates. That will give you a 55% share inflation. And the aggregate logit, if you were just to run aggregate logit, you'd get nearly a doubling in share if you entered identical products. So you can see, by virtue of estimating individual level data and capturing heterogeneity, that helps reduce the share inflation, the IIA problem, quite a bit, but it doesn't completely go away. Let's make some additional notes about the red bus, blue bus issue, okay? Like we said, simulating on individual level utilities reduces the share inflation problem a lot, but it still exists, okay? It still exists into a modest amount. Let's look back on it again. 55% share inflation, so two identical products adding leading to 1.55 as much share as before. So it does lead to share inflation for similar identical products. But on the other hand, you might think that for your particular product category and in the real world, maybe some share inflation for similar products is justified due to the randomness and behavior of respondents who aren't perfectly utility maximizing and able to discriminate and scrutinize all of the product offerings to ferret out those near product alternatives. Okay, the other thing I want to call your attention to is the more products that you have in your market simulation and the smaller the shares of preference for each product, the greater the share inflation problem. That is because if we only had 2 product alternatives and and each respondent is allowed to vote, each respondent probably gives 80%, typically will give 80% or more of their vote to their favorite product, just due to the scaling, the larger magnitude scaling of the HP utilities at the individual level. So if you duplicate that preferred product, it was previously getting 80%, there's no headroom for it to suddenly get 160%. It's got to tap out at 100% share of preferences. So you're not going to be able to increase the share of preference that much, okay? So, but as you can see, if you have a lot of products in the simulator, let's say 20 or 30, then each respondent maybe is only giving 30 or 40% of the vote to their favorite product, and adding a duplicate of it now has a lot of headroom to be able to increase the net share of preference for 2 alternatives when their shares start out as a much smaller proportion of the 100% pie. Now, Let me talk to you about price sensitivity curve kinks. Okay, weird distortions that can happen when we set up our price sensitivity curve simulations via sensitivity analysis in market simulators. What we typically do, not all the time, but it's typical when we want to simulate shares of, where we want to simulate, let's say, demand curves for different SKUs, for different levels of brand. We typically set all of them in the base case scenario at the middle price point. This causes them all to kind of load up on similarity in terms of the price point. And then when we take each SKU one at a time and we leave the others constant and just change the price for one of the SKUs, that can lead to some interesting kinks if we're doing a lot to correct for product similarity on the price attribute. Let me show you how that works. We have a setup here. Here's my setup. I've got 18 products in a simulation scenario. I'm still using the data set that I've described, the vacation data set, but I've got 18 different products that have different attributes and levels for the vacation. But I'm initially setting them all at the same middle price point, price 3 out of 5 prices that I included in my experiment. Now I'm going to change the price for the test product, holding all the other 17 products at their middling price, and I'm going to plot what happens to plot the demand curve for that test product holding the other 17 products at price 3. This is what the price curves look like for that product holding the other 17 constant at price level 3 and just varying its prices across the 5 price points. Let's start with the curve that we trust the most. That is this blue curve that's kind of going along the bottom. It's partially being hidden by the red here. But this is the curve that we trust the most because it uses point estimates, the share preference rule. In the past, we've seen that that's very similar to the curves that we would get from aggregate logit or from the counts analysis. We've learned that over the years that running share preference on the point estimates is a nice and faithful representation of the price sensitivity curve. Now let's look at the bad one here. That is the purple one. That's using randomized first choice on the point estimates, where we have where we've not followed what the software wanted us to do. We've ignored the warning messages about applying correlated error to price, and we have decided that we're going to apply the correction for similarity on the price attribute as well. What happens is when the test product moves away from price number 3, it gets a big reward through the randomized first choice iterative process. It gets a big reward for being unique. And that reward overrides the penalty for increasing the price to level 4, and we get this weird kink and this weird reversal around price level 3. Now, interestingly enough, using the draws and using share of preference gives us a similar kind of kink, but not as quite as pronounced. But if we use point estimates where we turn off the correlation for price, that's this red line, we get something much safer and much closer that we expect to be true, that we know to be true. So that's why Sawtooth Software recommends turning off the correlation for price for correction for similarity. And when you think about it, price is the thing that you give up for to get the features of a product. You think that features such as brand and color and form factor are going to matter a lot more to penalize products that are similar rather than price, which is just the economic value of what you give up to get the features of a product. Now, I haven't shown first choice on the draws on this, but first choice on the draws, we ran it as well, and we found that it provides an even kinkier, weird result than first choice share preference on the draws. It's kind of somewhere between the green and the purple lines, but with a weird kind of yucky kink here. And so first choice on the draws can create a pretty bad distortion, almost as bad as randomized first choice if you've got the correction for similarity on for price. But as long as you follow what the Sawtooth software wants you to do by turning off the correction for similarity for price, you're not going to see that weird kind of kink with randomized first choice. But the kinks exist in the draws, whether you're simulating on first choice on the draws or share preference on the draws, you can get a little kink around that if you set up kind of this scenario where you load a lot of products, all of the comparison products, all on the same attribute level, level 3 for price. You can get these weird distortions. Another weird distortion that you can get with draws was referred to back in 2010 by Kevin Carty at the Turbo CDC seminar. He talked about a tail effect bias that especially occurs if you like to fit linear coefficients to price. Now that's an advanced thing to do in our software, but you can fit linear terms to price rather than the part worth terms. And you will find typically that a significant % of the draws across respondents will show a reversal on the price coefficient. That typically will happen due to the variance in the draws and the fact that some respondents just aren't very price sensitive. And those draws that show a reversal on price on the linear coefficient can give you a strange upward bias in simulating the most expensive products at the highest price points. This pops out at you when you do linear coefficient estimation, and if you don't constrain the price, the coefficients to be negative, okay? So be careful about that unless you're constraining the price to be negative. Fitting those linear coefficients and trying to build simulators on the draws can give you this weird effect out in the tail in the upper price range where expensive products just get way over predicted in terms of their share. So, bringing some of the points together and emphasizing them, building simulators on the individual level utilities, like from hierarchical Bayes or similar, decreases the IIA problems significantly, but they don't go away. And the IIA problems grow as the number of products in the simulation scenario grows. So as the share preference for each product gets smaller and smaller, its share inflation for having similar products in there will grow. Randomized first choice can reduce the IA problems a lot, okay? And it can be applied to utilities estimated in any way. You don't have to have hierarchical Bayes utilities. We can have ordinary least squares utilities, aggregate logit utilities, HB utilities, latent class utilities. You could have developed utilities from a self-explicated models based on rankings and ratings, and you can apply randomized first choice. So randomized first choice is this general purpose, flexible, convenient because it's built into Sawtooth Software. And by the way, when you build Excel simulators, you can deliver the RFC plugin that Lighthouse Studio will create for you, and Lighthouse Studio creates your Excel simulators that you can even deliver randomized first choice simulators to your clients in Excel, as long as they're willing to install that plugin. Okay, so it's extremely flexible, can apply to all types of sets of utilities estimated in any way, and it does a very good job of correcting for similarity, and is tunable according to how much attribute error and product type error that you give to it. Other points that we'd like to drive home are that simulating on the HB draws is more defensible in the academic tradition of HB, but it would take longer than randomized first choice with bigger file sizes. And for the best data set that we have for testing the validity of different conjoint models and simulators, the 2016 prize that we put up, the predictive results just don't differ hardly at all between randomized first choice versus simulating on the draws. You can get some strange kinks in sensitivity curves and standard sensitivity simulations if you simulate on the draws. And this kind of really dramatic tail effect bias can occur if you fit a linear coefficient to price and don't make it, and don't constrain it. A log linear fit of the coefficient to price, because it creates this concavity for an upsloping demand, for a reverse demand curve, or for a reversed price curve, will help ameliorate that some, but it still exists, okay? First choice on the draws, if you want to do first choice on the draws, you're welcome to it, and you won't get any any share inflation for identical products, but it's not tunable. The scale that you get is the scale that you get, and you can't tune the exponent. It won't matter. Okay, now you could go back upstream and re-estimate the utilities under hierarchical Bayes using different prior variance settings, for example, and degrees of freedom, and you might be able to get a little bit different scale factor on the first choice simulations if you were to re-estimate the HB utilities in a different way. But you're pretty much stuck with the scale that comes out of with first choice on the draws, and it's not tunable. What about using the standard share of preference, the logit equation that you're all used to doing, exponentiating the utility of the product over the summation of the exponentiation of the utilities of it and the remaining products? Well, if you're building your own market simulators in Excel, and that's what you typically do on hierarchical based point estimates, then the good news is you're pretty much doing okay, as long as you're using those individual level utilities, and if you believe that a modest degree of IIA and share inflation behavior should be in effect for what you want to predict for predicting how the market behaves. But watch out for the IIA meltdown that can occur with big simulation scenarios involving dozens and dozens of product alternatives, because that share inflation, because you're building it on the logit rule, even though you have individual level utilities, is still going to be in play and is going to get more and more it's going to be more of an issue the smaller the shares get and the more products that you have in the simulator. So, wrapping it up, people might say, well, Brian, when would you not use randomized first choice? If you're going to have a 2-attribute study with brand and price, it doesn't make any sense at all to run randomized first choice. Randomized first choice is doing nothing for you. Okay, because randomized first choice thinks that each different brand is unique, and typically with a brand price study, you only enter each brand into the simulator once. So, and randomized first choice is going to recommend to you, for the reasons that I showed you about the kinky demand curves, it's going to recommend that you turn off the correction of similarity for price. So there's no, in a simulator involving brand and price, there's no opportunity for randomized first choice to correct on product similarity, because all the products have unique brands and we've turned off the correction for product similarity for price. So all you're doing to yourself is making yourself wait longer, because randomized first choice takes longer than the share preference rule. You're not getting anything. So don't use randomized first choice with a 2-attribute brand price market simulation in Sawtooth Software. Okay, people might ask me, well, Brian, when would you think that you wanted to simulate on the HB draws? You talked about how it was more proper for the Bayesian statisticians, and that's true. And that's why if I was going to be presenting the results at an academic conference, or if I was going to be defending my PhD in front of a Bayesian statistician who was my advisor, I would want to be creating a simulator based on the draws, because otherwise I'd probably get thrown out of the room, okay? But you know, as we've seen and shown, practically the results are not very much different at all compared to simulating on the point estimates. And as we thought about this, as I thought about this in the last couple of weeks as I've been preparing for this webinar, I've thought about 2-attribute studies involving lots of SKUs and price, where randomized first choice, or you know, we're not going to use randomized first choice on that, because each SKU is only represented once in the simulator, and randomized first choice would think that those SKUs are different. Well, within each respondent, if we're running HB, the draws will show a correlation between, for example, Coke Light and Coke Zero, 2 SKUs that might be viewed as somewhat substitutable and different offerings within the same brand. So maybe it's possible that by leveraging those draws, we could enhance the degree of substitution or sourcing effects, sourcing rates, between a simulator that was built on the point estimates versus a simulator that was built on the draws. And so we did an investigation with 2 recent data sets, a 39 SKU data set, brand and price, and a 51 SKU data set. I know that second data set is a beverage study. The first data set was contributed to us by one of our users, and we don't know what the product category is there. But we found that simulating on the draws versus simulating on the point estimates under the logit equation, the share preference rule, gave us essentially the same strength of sourcing or substitution effects, whether we did it one way or another, with just a tiny, tiny, tiny edge towards simulating on the draws, but not much of a difference to make much of a matter and care about for all practicality. So, you know, would I simulate on the draws? if I was careful about about that tail effect issue, if I was careful about not fitting a linear term to price and seeing that kind of tail effect bias, if I was careful about not setting up all of my products to be all aligned on level 3, 17 of the products, and then the 18th product varies so that I get this weird kind of kink as I pull that one product away from the similarity of being on the same price points as the others. Because there are some gotchas with simulating on the draws, but for the most part, you're going to generally be safe doing it, but not in that much better state at all compared to simulating on the point estimates in the looking that we've done. Now, I'd be very interested if somebody could come out to the Sawtooth Software Conference and show us instances where they really do see big differences between simulating on the point estimates versus the draws. I really haven't found it so far, but I'm willing to be corrected. So please do think about that. And if you strongly feel opposite of the position that I'm stating, please come out to the Sawtooth Software Conference and show your results. In terms of the last slide, I have ignored a number of other models that can be brought to bear, both for estimating the utilities and also building simulators for dealing with the IIA issue. I haven't talked about the top N share preference rule that was presented by Kees van der Wacht in 2014 and is available in Sawtooth Software's Lighthouse Studio Simulator. If you go into the share of preference rule and click the little settings button, gear icon next to it, you can modify the share preference rule to only give share to the top N products where you specify what N is, and the remaining products all get 0. There's also something called the post hoc nested share of preference rule, also presented by Kees van der Wacht in 2014, and also described in detail in Keith Shun and my book called Becoming an Expert in Conjoint Analysis. This is a way to post hoc create some nests of products that will compete and source from one another within the nest stronger than outside the nest. It's a post hoc method of taking your standard HB utilities and creating some nesting. If you want to do it more formally upstream, you might think about running a full nested logit type estimation. And that was described in several presentations by Kevin Lattery, but starting in his 2013 presentation at the Sawtooth Software Conference. With that, that wraps up our presentation for today. Thank you so much for coming. I know it was fairly advanced, but I hope that those of you who are building your own simulators and ponder as you lay on your pillows at night, whether you should be simulating on the draws, whether you should be using randomized first choice, whether using the logit rule, the logit equation on the point estimates is just fine or not. Hopefully I've given you some fodder to ponder and maybe giving you some assurances that what you're doing is working out pretty well. So thank you for listening. And with that, I'll turn it back to Aaron to wrap up the session with any housekeeping details.
All right, thanks, Brian. Let's see, let me look at time here. Yeah, so we got time for maybe 1 or 2 questions here. Can you talk a little bit about the actual variance? So, you know, with randomized first choice, we're going to be drawing error terms. Can you talk a little bit about what the actual variance is that we typically see in the data itself?
Without the error terms, does the typical variance across respondents?
Yeah.
Okay.
Well, the specific question is there a rule of thumb for the actual variance?
The actual variance of the respondents is just going to be due to how much heterogeneity and heterogeneity of tastes there are in the respondents. Now, of course, so that's something that you can't change. The respondents come to you with their preferences, and they might be very similar across respondents or different across respondents. What you can change is the prior variance assumption in hierarchical Bayes. In the advanced settings of hierarchical Bayes, you can specify the prior variance, which by default is 1, and the prior degrees of freedom, which by default is 5, which is an influence of how strongly we impose the prior variance. If you want to influence the hierarchical Bayes results to have higher variance across people, then you increase the prior variance setting, and perhaps you increase the degrees of freedom setting to something greater than 5. This can give you greater variance across respondents, but it also can lead to overfitting. And Walt Williams and I gave a presentation at a previous SCIM conference, and the paper is available at the Sawtooth Software website, where we looked at 50 different data sets and looked at different tunings of the prior variance. You can tune up the prior variance and get more differences across people, but that typically will lead in our sparse data sets to overfitting, and you're shooting yourself in the foot.
Okay. And is there a rule of thumb for how much variance you want to add in during the randomized first choice process?
You typically want to add the amount of variance in those random shocks that will lead to flatness or steepness of the shares similar to what you get from the share preference rule. So if you're doing your own tuning in Excel or something, because you're building your own randomized first choice simulator, put in products in the scenario that don't have any levels in common, and then run the simulation under randomized first choice and run it under share preference logit rule, and then tune the amount of variance of the random shocks that you're adding to randomized first choice until you get those shares to as closely align in terms of flatness or steepness with the regular share preference rule. And because none of the products share any of the same attribute levels, there's no correction for similarity happening. You're just tuning the variance at that point. And then you move into your regular simulations where some of those products are going to share attribute levels in common, and you're going to get penalties and so forth.
Okay. Okay, can you suggest a rule of thumb on minimum number of competing products where you should consider using randomized first choice versus draws?
Well, as we add more and more competing products, the shares get smaller, and those kinks on the demand curve can get bigger, and the share inflation can get bigger. I haven't looked at that deeply. I know that the people that I've talked to, when they think about IIA meltdown, they definitely think about IIA meltdown and having to do some sort of nesting or some sort of additional, bringing some sort of heavier hammer to bear on it with some sort of different model that recognizes nesting if they have more than, let's say, 50 or 100 products in the simulator. That definitely leads, as academics have presented at the Sawtooth Software Conference and practitioners as well, leads to IIA meltdown. Whether IIA meltdown is going to be hitting you smack in the face with 12 products in the simulator, you know, there is some IIA, it's a sliding scale. So honestly, I just haven't looked at it deeply enough other than to know that those who've looked into this definitely call out 50 or 100 product simulators as having IIA meltdown. And those of us who are using a dozen or fewer products in a simulator typically think that we're doing generally okay without any fancier model.
Okay, so somewhere between a dozen and 150.
Yeah.
Okay. All right.
Sorry,
Okay.
You can't be more definite. And he's going to compare, you know, project to project, it's going to be different depending upon the heterogeneity of the sample and how many choice tasks you add, you collect each respondent, to how much heterogeneity you can wring out without overfitting, et cetera, et cetera.
Yeah. Okay, a couple more questions here. You talked about a kink in the point estimates when price goes from like level 3 to level 4. What could be the reason for the kink, and could you solve it by putting a constraint in there?
Okay, the kink particularly happens with randomized first choice as, when you think about it, if you have 18 products and they're all aligned on that third price point, the kink happens when you don't follow the recommendation and you keep on correcting for similarity with a correlated draw on price. All 18 products are getting the same correlated draw for the price part of the part worth function. Now, when one product moves off, even if it moves to a lower price utility for the deterministic part of utility, moving from price 3 to price 4, it's getting a random perturbation on it that sometimes allows it to exceed the utility in the first choice rule of the other products that are all lined up and getting the same draw. So the fact that you get this unique draw on price for the one versus the other 17 that are all getting the same draw on that price coefficient means that even if you constrain the price to be negative, you're still going to see this weird kink. Constraining price to be negative doesn't solve it, and doesn't solve it either with running HB on the point estimates. Even with constrained price, you're still going to see some weird kind of kinking behavior around around that middle price point when you set all of the products to be equal on it. Now, the kinking is not going to happen as dramatically with the constrained HV draws as it will be with randomized first choice, but it still distorts and kinks.
Okay. All right. Last question is, do you have instructions somewhere on how to import the draws into the Lighthouse simulator?
Oh, the easy way to do it, you don't even need instructions. You know that, that when you run hierarchical Bayes, that it will give you that utilities file that we typically use, which just has one utility for each respondent, the point estimates. Just look at its format and then open up your draws file and just have the two open in two different windows, and then make your draws file have the same number of columns and the same labels and the same information as the point estimate file has. Just make it have the same format and you're fine. It just takes a couple of minutes of modification in Excel.
Yeah, just note that like if you have 500 draws per respondent, you're going to have 500 simulation results per respondent also. So some of your statistical tests that take into account sample size are going to be off a little bit. So
your standard errors are going to be vastly wrong.
Yeah, yeah.
Your standard error is going to be really, really tiny when they should be a lot bigger, because we're going to be exaggerating the sample size in that equation.
Yeah. Okay, I think that's all we have time for. Thank you so much, Brian, for your time today and for your observations. And let's see, the next webinar will be on October 29th. We're still working on the topic for that one. We should have something announced in the next couple days here. So we'd love to see you then. We'll be posting information about that up on the Sawtooth Software website under webinars. Also, remember that we will have the presentation materials and a recording of this webinar available typically within about 24 hours, maybe a little bit longer. We should have that up in the next day or so. So thank you again for attending, and we'll see you at the next webinar.